We have here a differential equation, and our objective first is to try to transform this differential equation into a new differential equation by making use of the substitution w is equal to x times y. And if we were to take a look at the new differential equation, this new differential equation consists of x and w, which means that we are going to try to substitute and replace all the y's in this differential equation. So let's do that by first finding a way to substitute dy dx. We can start by maybe doing an implicit differentiation to this with respect to x. So differentiating w with respect to x is dw dx, and differentiating this with respect to x by applying the product rule, it is going to be x times of differentiating y with respect to x, get us dy dx, then plus differentiating x is 1 multiplied by y. So we can definitely make dy dx a subject, and whatever that is on the right hand side of the equation, we will just substitute and replace this, okay, which is fine. But if we can just include a bit of observation and analysis to what we have here, there is a x dy dx here, and there is an x dy dx here. And if we were to bring minus y over to the left hand side, we will actually get an x dy dx plus y, which can be very efficiently replaced by dw dx. So let's just do that. So we will get a x dy dx plus y is equal to this. Okay, now on the right hand side, we have a xw. xw is very efficiently replaced, right? Because it can be replaced by just w. But how about this ln x plus ln y? Again, if we can just take a moment to observe and implement a bit of our algebraic manipulation, or more specifically here, apply a bit of the law of logarithms, then this can be rewritten as ln of x times y, and xy is just simply going to be equal to w. So we now have another equation, okay, which is actually this, but it is manipulated in such a way that it makes substitution so much more efficient. So this is going to be replaced by dw dx, and this is going to be replaced by w, and here we have a ln w, and this is what the questions require us to show. And if I were to compare this to what the question wants, this will be fw. So let me write it down here, where fw is going to be equal to w ln w. Okay, this is for the first part of the question. And for the second part of this question, we are going to solve the differential equation. And of course, we are going to be making use of our new version here to solve it first before I try to relate it back to the original one. So let's try to solve this differential equation. Let me rewrite it again. dw dx is equal to w ln w. So this that we have here on the right hand side is a variable separable format, where we can see this as a function in terms of w multiplied by a function in terms of x, which happens to be 1 in this case. So according to the method that we have to solve this differential equation, which is a first order variable separable differential equation, we're going to divide this over to the left hand side, giving us a 1 over w, then ln w dw dx is equal to 1. And then integrating both the left and the right hand side with respect to x. On the left hand side, it's going to be reduced to 1 over w ln w dw is equal to integration of 1 with respect to x. And to integrate this, we're going to apply f prime, okay, where f is ln w, f prime will be 1 over w. Let me just rewrite this. So 1 over w is the f prime, and w is going to be, and f is going to be the ln w. Okay, so dw is equal to integration of 1 dx. So let me continue here. For what we have here, it is going to be a ln modulus of ln w is equal to x plus an arbitrary constant a. W is equal to xy. So we have a ln modulus of ln xy. This is equal to x plus a. So modulus of ln xy is e to the power of a, e to the power of x. Okay, if I have to break this up via indices into two parts like this, so ln of xy is going to be plus or minus e to the power of a, e to the power of x, which I am going to re-express this as just simply b, e to the power of x. Okay, way more efficient to try to consolidate all the arbitrary constants and the constants, if they were to be together into another alphabet. So where this alphabet B will be representing now plus or minus e to the power of a. We are going to make use of the information that is given to us by the question to solve for B. The question says that when x is equal to 2, y is equal to 1 over 2 e to the power of 3. So let's substitute this in. Okay, so it is going to be ln of x, which is 2 multiplied by half e to the power of 3 is equal to be to the power of 2. And this is going to be ln e to the power of 3. This is be to the power of 2. This will just be 3 ln e. Ln e is going to be equal to 1 anyway. It's equal to be to the power of 2. So b will be e to the power of 2 divided by 3. Okay, so now we have this, and oops, I'm writing this wrongly. b is going to be 3 divided by e to the power of 2. Let me just correct this. So it's 3 divided by e to the power of 2. Okay, let me substitute this back into here, okay, because according to what the question wants, we are going to try to get our solution to this differential equation where y is the subject. So substituting back into here, we have a ln xy is equal to b, which is 3 over e to the power of 2, e to the power of x, which I think for this, I'm going to just rewrite this as 3e to the power of x minus 2. So xy will just be e to the power of 3, e to the power of x minus 2, which means that my final answer will be y being equal to e to the power of 3, e to the power of x minus 2 over x.